In this lecture we define a functor. So functor is a mapping from category C to category D. So you have category C here, you have a category D here, and functor is just a mapping. So it will take an object A in category C to f of A, which is an object in category D. And then say you have a morphism like this arrow in category C. This is a morphism. So say this is f. So this is carried out to this arrow, this f of f. And then further, if you have another arrow like this, I mean naturally you will have this thing f of g here. So now you know this composition. You first apply f and then you apply g, and here you first apply this and then you apply this. So if you apply the functor f to this arrow, this entire thing, that will be, so we want these to be equal. So whether you go this way or you apply functor f to this, these two should be equal, and that is all what a functor is. So to each object A in category C, this functor will assign an object f of A in category D. To each morphism in category C, this arrow in AB, this is also written as home, you apply a morphism f of A to f of B. So precisely this one, and this is an arrow in the category D. So this is an arrow in the category D. Now this is also to satisfy one more condition, that f of id on A is id f of A. So that is, you have a map here which is identity. This identity has to be carried to this identity. So identity on f of A. So precisely what you think it should be. And if you are given morphisms like this, A to B and B to C, A to B, F, and then B to C, this should be carried to something like this. So this thing is carried here, and then the composition law, f of g of f. So you have g of f going like this, and this gets mapped to this, and this should be precisely the composition of this f of f and then f of g, that is composition of these two. So this is all what a functor is. So in this lecture we are writing functor like this in a calligraphic F in green, but we can also write functor like a straight letter F. It will be clear from the context whether this is functor or not. But in this lecture and in some of the other lectures we will write it as this calligraphic letters with color green. Now let us give some examples of functors. So this is a category here, this is a category here. So this category is carried to this category via the functor here. So topological spaces, the category of topological spaces, you apply fundamental group to it, you end up in category of groups. So again you take topological spaces, you apply the homology functor to it, you land up in groups. Again topological spaces, apply cohomology functor to it, you land up in groups. So notice you have this n here, n here, n here. So for each n there is a different functor. So for example, so you have S1 here, which is a topological space. You apply H0 to it, that is homology functor, you get integers which lies in groups. Now again you can apply H1 homology functor to it, you will again get integers. Then you apply functor H2 to it, you will get 0. You apply H3 to it, you will get 0, and so on. So for each n there is a different functor. So here you have, countable functors here, countable functors here, countable functors here. For every n there is a functor, so you need to keep that in mind. So again you have linear presentation, so groups can be turned into modules. Then you can take a module to its dual space, so k module to a k module, which this module is dual of this module right here. So this is a dual space functor. Then you can take a group A and associate with group A some free group. So this is a free group functor. It takes a group A and associates to it a free group. And then there are a set of forgetful functors. It just takes spaces to underlying elements, takes groups to its underlying set. So this is the underlying set. It takes topological spaces to its underlying set. It takes rings to its underlying set. And then you have this important class of functors called contravariant functors. So contravariant functors keep every object as the same. Only thing they do is they reverse the arrows. So you write it as C op, so that the arrows are reversed. So arrows are reversed. Now very important example of this contravariant functor is this pre-sheaf or sheaf functor. It takes open sets on X, and to each open set it associates a group. So for every open set you have some group O of U here, but the arrows are reversed. So if U is contained in V, you have the group homomorphism like this in the opposite direction. So see, this arrow goes from U to V and this arrow goes in the opposite direction. So pre-sheaf and sheaves are contravariant functors. Now we discuss two very important functors which show up in algebraic geometry everywhere. So consider this set of arrows from X to Y in category C. So notice that for defining a category, we said that the arrows form a set, and that's what we are using here. So basically we are working in a small category. So you have set of arrows, and you fix this, say, object X in category C. So you fix X in C. So notice that sometimes you write home XY as this. This is set of arrows. So you end up fixing this object in the category. And we have this map from category to the set. So this is set of arrows. So what does it mean? You take an object Y lying in C. So Y is an object of the category. So Y is object of category C. And then you apply this functor to it, and it will land into set. So what does it mean? To every object Y in C, it associates the set of arrows going from X to Y. So home X to Y, set of arrows. So this is set. So this is set. So that's why we are landing in the category of sets. So consider the set this. So this is very important functor. So this is the functor which is always used when you land in the category of sets in algebraic geometry, or most of the time. Now let us see the morphisms. So say you have two objects y1 and y2. So this side is in category C and this side is in category of sets. This entire side is in category of sets. So now you pass on to the category of sets by applying this functor. You get this arrow again y1 to y2 G, and you have arrow from X to y1 which is given as F. So now you can compose F with G to get first apply F and then apply G. So you have a morphism which takes arrow from X to y1 to an arrow from X to y2. So you're taking this arrow to this arrow via this map G. So G is given to you, so you have to use G. So this is what it is. So you're taking the arrow X to y1, this arrow is right here, to arrow this arrow is right this arrow via this map G. So instead of this dot we have put G here. So you write this functor as home X dot. That means arrows are going out from X into object Y. So this X is fixed. You could have another object, say G here, and then you have to associate with G an arrow in this category set. There will be an arrow from X to G. So notice that this is covariant, that it preserves arrow. So you have arrow going from y1 to y2 here, and here you have again y1 here and y2 here. Notice that there's y1 here, y2 here, and there is an arrow going from xy1 to xy2. So again you have preservation of arrows, directions. Again you're going from y1 to y2. Now let us reverse this process. Let us get something contravariant. So you do the same thing here. So now we will reverse the arrows. So we will land in the opposite category. So again you have same thing here, but now instead of having x in the first place, you have x in the second place. So again, to every object y in category C, you apply an arrow, but now the arrow goes into x. So to every object y, you have an arrow which goes into x. So for every morphism like this, an arrow between two objects y1 and y2 in category C, you'll end up in set like this. So this arrow y1 to y2 is there. Now the thing is, we want to use this arrow g just like we used the arrow g here. So notice that we used arrow g here. We want to use this arrow, but the problem is here you had this f going into g. So this is going in. Here you have something going out of g. So you can't really use g into this arrow right here. We can't use g into this arrow. So you have to use something else. So now you consider this arrow which is going out of y2, because here you can use g because g is going in here. Here you cannot use g. So you cannot use g here, but you can use it here. This is good. So you take this f1 and then you can get this arrow from y1 to x by composing this. So first apply g and then you apply f1. So you can compose this. So now you can go from this arrow to this arrow. So arrow from y2 to x to y1 to x. So you have arrow from y2 to x goes to y1 to x. And again we have, instead of this dot, we have put in g. So we have used g again. But notice now we have contravariance. So this arrow went from y1 to y2. But here you have the objects of this categories are arrows. So object of the category of sets is these arrows. But these arrows go from y2 to y1. So there is contravariance. y1 to y2, the arrow gets reversed. Notice that this is the contravariance here. The arrows get reversed. So these two functors, they keep showing up in both topology and geometry.